along to our next section. Is is the presentation up? Is the PPT up? Okay, good. Thank you very much. Okay, we're going to take a look at some of the various containment systems that are most commonly found in the carriage of liquefied natural gas. Uh, Here are the arrangement systems, types of containment systems, and then we'll take a look at the summary and conclusions. A total arrangement for containing cargo includes, we're going to look at what's called a primary barrier, and that usually consists of the cargo tank itself. And then there's a secondary barrier, if fitted. In most cases, there is a secondary barrier, associated thermal insulation, and the intervening spaces that we're going to find, the adjacent structures for supports of these elements in the ship. Okay, we're getting a little background there. For cargoes carried at temperatures between -10 degrees and -55 degrees, the ship's hull can act as a secondary barrier, may be a boundary of the hold space. Now, what this just simply means is there are some liquefied gas cargoes where we don't need cryogenic materials for the secondary barrier, and this would be for your heavier ends. For LNG, though, this is not the case. Since LNG is carried at minus 160 degrees, the ship's hull, their tanks have to be of a cryogenic nature. Now, we're going to have a video. I sent Jared the link for a video that was produced by the BBC, and there's 2 sections in there. It runs about 40 minutes. If you want to watch the whole thing, that's fine. But if not, that's okay too. What I would like you to watch is the first 5 minutes of the video, and then from 17 minutes to 24 minutes. The first 5 minutes is just a little intro, and the fellow who's doing the documentary, he actually goes inside a spherical tank on one of those large Moss carriers. And it's just kind of an interesting environment. It's something that most people will never ever get to see. In my experience, I've been inside these tanks many, many times, and I still get a kick out of it when you hear how it sounds inside one of these very, very, very large tanks. We're looking at tanks somewhere in the order of 36, 38 meters in diameter. It's just a very, very strange environment. So if Jared gets that link to you, it's the first 5 minutes, and then from 17 minutes to 24 minutes, which is going to be a demonstration of the conduct of materials when subjected to cryogenic temperatures. The first part of that segment is what happens to mild steel, ordinary carbon steel, when it's subjected to cryogenic temperatures and then struck with a force. And the second part of it shows what happens to a similar piece of material made out of stainless steel. And this is the this is the most common material used in cryogenic tanks, stainless steel or aluminum alloys, which react the same as stainless steel when subjected to cryogenic temperatures. The interesting thing about cryogenic materials is they become stronger as they get colder, contrary to what happens to mild steel. Mild steel is subject to brittle fracture. Cryogenic materials actually increase strength the colder they get. All right, the primary basic cargo tank types are called independent type A, independent type B, independent type C, and membrane. These are the 4 basic types of tanks. Remember these, please. Type A, Type B, Type C, and membrane. Independent type A and B. These are self-supporting structural tanks, and they're either full or part with a full or a partial secondary barrier depending upon design. They are extremely rugged, very, very rugged in design, and they're volumetrically efficient. No wasted space. This is a sample of a self-supporting prismatic IMO Type B tank. And as you can see, the tank actually is part of the structure of the hull, completely fills the hull. You have a centerline bulkhead, which virtually eliminates the sloshing. Again, this is structural steel in here, stainless steel or aluminum alloys, very, very strong. Then you have an insulation barrier that goes around the outside of that particular tank. You have the inner hull, and you have a ballast tank. So this is all an integral part of the actual construction of the vessel. The downside of this particular type tank, there are maybe only one or two, there's two or three carriers, I think, that actually have this construction. A, it's very expensive. And B, it adds weight to the ship. You have all of this steel in here. And that will limit the volume that the ship can carry, because most of your LNG carriers are draft restricted in where they can go anywhere in the world. The average draft of a LNG carrier, regardless of size, usually runs around 12 meters in draft. It draws 12 meters. Okay. Now, if that 12 meters, a lot of that weight is made up by steel, that's that much less cargo that you can carry. So even though this is an efficient type of containment system, it's extremely strong, extremely rugged and whatnot. It's not as economically efficient as some of the other methods. Okay, independent type A and B. There's a secondary barrier which requires gas monitoring, and the secondary barrier can actually be stainless steel. It can be a drip pan. Depends upon the type of a tank that we're looking at. The operating pressures of this type of tank is up to 15 psig, or about a bar. About a bar, a little bit over a bar. Okay. Because of the type of construction, you just can't dump LNG into this tank. You have to cool the tank down over a period of time before you can actually load LNG in the tank. And because of the nature of the tanks, they're unable to retain boil off for extended periods because you're restricted by the operating pressure of the tank. So you can't put cargo into it and just let the pressure inside that tank build up. You have to have a means to get boil up. Right. This is an example of the self-supporting spherical type B tank. This is a common, probably 40% of the LNG carriers in the world are of this type design. And it consists of a sphere, and the sphere is either stainless steel, aluminum alloy, a steel alloy, or whatnot, or a combination of all of these. So you have this cylindrical or this round tank. It's usually, okay, this has changed because they've now changed the design of these a little bit. But initially, it was a round tank, and it's supported in the hull by a connection to the hull, which is called at the equatorial ring of the tank. Tank actually joins and becomes part of the hull. But this tank is actually suspended within a hold space in the hull. And if one were to climb down inside the hold space of this ship, you could actually come down here and you can walk underneath the tank and around it. This type of a configuration is not as volumetrically efficient because you have a lot of wasted space. The hold, though, it can be kept in an inert environment, which is very, very advantageous and safe. The secondary barrier in this type of a tank, though, is a little drip tray that's underneath that sets underneath the tank. The theory behind a cylinder or a round tank or a circular tank is that the tank a sphere is always going to leak before it fails if this ever does happen. And if you do get a leak of liquid inside the tank, that liquid is going to hug the surface of the tank until it gets down to the bottom. And if there's any liquid left over, it will actually drip into this drip tray in the bottom, which protects the hull. These tanks have proved to be extremely reliable. There's some ships out there with tanks of this nature, 40 years of age, have been subjected to numerous cool downs, loadings, and discharge of cargo. And these tanks are inspected on a regular basis, X-ray inspected, and there have been no notes of any failures in these tanks. They are very, very, very robust. Then you have what's called a Type C tank, independent Type C. And these are the cylindrical tanks that we were talking about earlier. This is the type of a tank that you'll find on a tank truck, a cylindrical pressure vessel. And it's built to recognize codes, be they codes of the US or Europe and whatnot, and with low allowable stresses and no secondary barrier. These are extremely rugged. They're volumetrically inefficient because they take up space, and as is indicated, one of these cassette type things or one of these isotainers that we see. You have the container cell, which is square, and you're going to put this cylindrical pressure vessel on a skid, and it takes up the space it's taking up. There's a lot of wasted space. So in that respect, they're volumetrically inefficient. There's no secondary barrier required, and there's no gas monitoring required because of the design of the tanks. Here's two examples of what you might see on board a smaller vessel. There's small LNG carriers that travel, I know, in the Far East and Japan and whatnot. I suspect there are some in the European market as well. In this particular case, there's two cylinders. And in this particular case in here, it's a bilobe tank. Again, very, very, very strong tanks. But again, they are volumetrically inefficient because you have all this space around the tanks that is wasted. Independent Type C tanks, they have operating pressures up to approximately 10 bar, 150 psig. So these are the ones that you can do a pressure transfer of liquid from the Type C tank to wherever it's going, to the receiver. They do require a controlled cool down, though, because you're talking a very robust material. You're talking about a thickness of steel, and you just cannot introduce LNG into a tank of this nature. You first have to admit cold vapor and let the inside of that tank cool down slowly and equally over a period of time. Because of the way the vessel or the way the tank is constructed, and it's able to retain boil off for an extended. Obviously, if the pressure is allowed to increase up to 10 bar, that is take a long period, so it does retain boil off for extended. The next type of a tank is a membrane tank, and this is the probably about 60% of your LNG carriers in the market today are of the membrane type. And there's a primary and secondary barrier, and there's insulation systems in between. We'll see a diagram of those shortly. And the insulation system is supported by the ship's hull. It's affixed to the hull of the ship. There's a pressure differential between the barriers, and they are volumetrically efficient, using just about all the space available to store cargo. The actual steel in these tanks is, it can be stainless steel, and there's usually 2 layers of stainless steel in the tank, and they run about 0.7 millimeters in thickness. So very, very thin, very, very strong. You also have a material which is called N-bar, another type of membrane tank. Again, very, very thin. The N-bar is about 0.7 millimeters. The stainless steel is about 1.5 millimeters. Sorry, but again, these materials are extremely strong, very thin, though, so you're not taking up a whole lot of space and weight with the material that the tank is constructed. All right, this is a shot of GTT, the Gas Transport Technogas. Originally, there were two companies. One was called Gas Transport, the other was called Technogas. They were competitors. They have since merged and have combined their technologies in a very, very efficient system. As you can see, these boxes that are here are actually made out of wood. They're plywood boxes. This area here, this is filled with perlite as the insulation, and you have a layer of your tank, be it the Invar or be it the stainless steel. This is again topped off with another box that's filled with perlite, the insulation, and then you have your inside layer of material, which is the primary barrier. In this case, it's Invar. So you have a primary Invar barrier, insulation, followed by a secondary Invar barrier, followed by insulation, and all of this is affixed to the ship's hull. The barrier spaces require gas monitoring, and they are monitored 24 hours a day, 7 days a week by your gas detection. The operating pressure of this type tank is less than 5 psig. Tanks can be cooled down quickly. This is one of the advantages of a membrane tank. Since the material that the tank is constructed of is so thin, you can cool them down very, very quickly, and that's done by spraying LNG into the tank through a series of spray nozzles. And once the temperature of the material inside the tank is approximately 130 minus 130 degrees C, you can then begin loading liquid in. When you're dealing with the spherical tank, you're talking a large amount of mass that has to be cooled down. One of the disadvantages of the spherical tank is that it takes a considerable length of time to do a cool down of one of these tanks because of the mass involved. You're looking at a thickness of approximately probably about 2.5 inches, 50 plus millimeters at the bottom, up to 8 inches at the equators, and 1.5 inches at the top. So you've got all of this mass that has to be cooled down prior to the introduction of liquid into tanks. So cool down for a spherical tank could take upwards to 40 hours, 48 hours, something in that area. You can cool down a membrane ship in about 8 to 12 hours. I think the different time required, the quantity of product required to ship down. This is a shot of the inside of a membrane tank. You can see it's prismatic in design. Go around the tank here. This is the pump column. This is where your main cargo pumps are located. There's usually 2 main cargo pumps, and then there's an emergency pump column as well, and a small column for a pump that's called a cool down or a spray pump. So all of that is contained within this column arrangement, which is affixed at the after end of the tank. You can get an idea of the size of the tank by taking a look at the little fella standing over here, left of the pump column. Pretty impressive stuff when you actually, and as you can see, it's nice and shiny, nice and clean. It makes little difference whether this ship is brand new or whether it's 15, 20, 30 years old. Climb down inside that tank and it's going to be almost identical to what you see here because of the nature of liquefied natural gas. Very, very clean product. Okay, the construction of your containment systems is regulated by the International Gas Code, right? We have the MSC code, the IGF code for vessels fueled by LNG, but again, that only applies to the construction of the ship. It doesn't apply to transfer of LNG, only to the construction. Same thing with your International Gas Code. This applies to the construction of the ships and the containment system. Doesn't apply to terminals or shore-based. So the IGF code requirement is close as possible to the center line of the ships. A minimum of B divided by 5, the breadth of the ship divided by 5, and 11.5 meters from the ship's side for where a tank or an actual containment system begin. And it's a minimum of the breadth divided by 15, 2 meters from the ship's bottom. So the tank is basically at least 2 meters from the outer skin of the ship before you actually reach tank on the bottom of the ship, and 11.5 meters from the side inboard. That space is usually taken up by your ballast tanks, segregated from your liquid, totally segregated. All right. The IGC code requires that the tanks be separated from your machinery spaces by a cofferdam of 900 millimeters in thickness with A60 insulation. That means that a fire should be able to burn on that one side of that cofferdam for up to 60 minutes with no degradation of the additional U.S. Coast Guard requirements are the tanks shall not be located below accommodation spaces, service spaces, or fuel stations. Your tanks are going to be separate from your living area, from your machine area. This is by regulation. All right. This is an example of a proposed design. This is from Wärtsilä. Here's obviously our diesel engines and our alternators and whatnot. And this is using an LNG stack pack of Type C tanks, which are connected to a manifold area, which is right up here. As you can see, the tanks are not underneath the accommodation area. They're separated from, and there is a cofferdam in here to separate this area from the machine base. This is another example of a containment system. This is one of those what we talked about was a set type system where you have this C-tainer Type C tank in a 40-foot bed or a 20-foot bed locked into its space here. And here's your fuel manifolds, and you have a short connection piece right here, which is most likely done with some type of a dry brake coupling. The LNG containment systems are basically very large. They're a lot more complex. But they're a big thermos bottle, basically, what it is. It's more it's easier to compare a spherical tank with a big thermos because it's a round thing and it has insulation around it and whatever's inside is kept cold. And these containment systems are used based on traditional but also new and emerging technology. There are new type of insulations being tried by GTT and other ones to reduce the boil off that LNG carriers are subjected to. You have to allow the cargo to boil to keep the cargo cold, but you want to be able to minimize that boil off because every bit of gas that's produced and boil off has to be disposed of in some way. So you want to minimize that, keeping the cargo temperature cold and keeping the pressure within maintainable limits. So technology has improved, insulations have improved. The earlier ships had a boil-off rate of usually I think it was about 0.25%. In actuality, it ran around 0.18% per day. Total volume was boil-off. Your newer insulations are more efficient, and they're actually down to as low as 0.12, 0.11% boil-off. So as time goes by and materials improve, we see greater efficiencies coming about, and these efficiencies are important because all of this boil-off gas, all of the gas has value, no matter where it is in the value chain. Interestingly enough, when these LNG projects first started, when a vessel went into a loading port and loaded cargo, the boil off used to go to a flare. It used to just be flared off because initially in these projects, the vapor return was seen as not of any particular value. But of course, as the price of energy has changed, the price of oil, price of gas, everything has changed. The economics has changed drastically. Now everything is seen as having value. So very, very little wastage is in the industry. Is in the industry. Okay, another good question I have here. What kind of weldings are used in the assembly of the shells? And do I consider residual stresses caused by the welding process during the design of the vessel? Yes, these are all considered in the design of the vessel, the design of the tank. Uh, everything here is robotically welded and then inspected, X-ray inspected, die checked inspected. There's numerous tests and whatnot done. All of your stresses, though, are calculated process done during the process. Each containment system is designed and constructed to meet the operating needs of the LNG supplier and the eventual cost of building, acquiring, and using these containments must always consider safety as the number one priority. Okay, that's it. Jared, I sent you a link. And for section 3.5 on the LNG containment systems. And if you would give that to the participants, I'd appreciate it. And that's the one where if you do view the 0 minutes to 5 minutes, and I think it's 17 to 24, you get a pretty good feel for what a spherical tank is like on the inside. And you'll also get a very good feel for the ductility of materials. That last section is a good example of what happens to materials when they're subjected to cryogenic temperature.
Hey, John. Jared's here. Would you like the students to take a break and watch that before they return, or did you want to just wrap up earlier than 5 and allow the students to watch after we finish the day?
Yeah, I think I'll just roll through, and if there's any questions, you can hit me with them first thing in the morning.
Outstanding. We sent the links over to the students, so they should have those. If you have not gotten that, please send an email to jam@wmu.se. That's Josephine, and we can get that link out to you and all the other documents as well. Okay.
All right, as we'll move along here. .6. All right. Set PPT up, section 3.6. Okay, Jared, do we have that PPT up?
We're okay from our end. I think you're all set.
Okay, good. Okay. All right, let's take a look at something that's very important in the handling and the loading, discharge, and carriage of LNG, and those are the various types of instrumentation and monitoring systems that we have. And we're going to take a look at gauging systems, different types of gauging systems, and gauging systems are the systems that are used to measure the volume of LNG inside of a tank. And this can be done using various type probes. using an ultrasonic device, radar devices, and we're going to look at some of the testing equipment we have, okay? IMO classifies gauging systems. There's two types, which are called indirect. And this is something we don't see in the LNG trade. It may either be weighing methods or flow meters. And then we have what are called closed devices, and these are the most common in the LNG trade. They're non-penetrating. In other words, they do not penetrate, they don't penetrate the tank itself, or there is a penetration, but it's within a closed system inside the tank. The ultrasonic and radioisotope sources may be used for the non-penetrating, and then you have penetrating types, which are the float gauges and bubble tube indicators. I've never seen a bubble tube indicator used on board a ship, though I have seen float gauges. This is a manual type gauge. It has there's a head that's outside the tank. It goes through a valve. There's a valve that isolates it from the tank. You can open this valve, and then you can lower a float, actually physically lower a float inside the tank until it reaches the surface of the liquid, and there's a readout up there which actually gives you the image of the tank, which is the depth of the cargo within inside that tank, and then we can take that figure and then calculate the actual volume from that figure. Then we have what are called restricted devices. These are the most common in the LPG trade. They penetrate the tank and they release small volumes of liquid or vapor to the atmosphere when in use. I, unfortunately, have never had the opportunity to work in the LPG trade, so I have no experience whatsoever with this type of gauging system. And the types of systems that they refer to here are what are called fixed or slip tube gauges, and when not in use, they're kept completely closed. Liquid level gauging is installed in each fuel tank, and they operate over the full range of fuel temperature and pressure. The indirect measurement devices, such as weight as flow meters, the direct measurement closing gauging devices, such as float gauges, capacitance gauges, radar, and ultrasonic gauges. We're going to concentrate particularly on just the floats, capacitance, radar, and ultrasonic. Flow meters is something I have not seen used with any great frequency. You may find them in loading terminals or a discharge terminal, but on board ship you usually do not find flow meters. Okay, the liquid level monitoring. There's two systems and two independent systems within the tank. All right, you have a system that includes a high level alarm, and this alarm, when it's activated, will close a fill valve to the particular tank in question. Each tank must have. So if we have a tank, if we have a gauging, or if we have a bunker, a vessel that has several tanks. Let's say it has 3 separate fuel tanks. Each tank must have 2 independent means of measuring the liquid level inside that tank, right? So we have the one that will be monitored, and if we get a high level alarm, it will close the valve into that tank, and then have an independent high level alarm, which activates an automatic shutdown. So one is totally independent of the other. We're not depending on one level gauging system to give us control over the amount of product that's going inside that tank. Okay, so here's an example of a float gauge. And this is what one actually looks like. Head of the gauge, which is the measuring device. You have a tape up here connected to the actual float. Isolation valve. Valve is when the float's in the stowed position, the float is up here. Open the valve and you can lower this float down until it reaches the surface of the liquid in the tank, and you get a local readout on a window up here, and you can take that local readout and go to gauging tables where you convert the image into an actual volume of the tank. Capacitance probes were used early on in projects. They are very accurate. No moving parts. That's a nice thing about a capacitance probe. So the property of an electric non-conductor that permits storage of energy as a result of the separation of charges that occur. This is complicated. The opposite surfaces of a non-conductor remain in the difference of potential. Basically, it's a tube within a tube, and you're measuring an electrical potential difference between the two tubes, and that changes as the liquid rises inside that tube. Uh, the input from that is it's transferred over to an analog to digital converter, and it comes out and it gives you a level. We had this type of measuring system on board the old Moss ships that I sailed on. Uh, the actual capacitance probes never had a problem with the probes themselves. The backup electronics, we'd occasionally have some issues, but they were very, very reliable. But they have basically given way to ultrasonic and radar as the primary source of measurement nowadays. So I really don't think you'll see that around too much. In all probability, you're going to see radar as the primary source of level gauging. Okay, good. The capacitance property that's equal to the, okay, again, we're talking about the capacitance, we're talking about the ratio of the charge on either surface to the potential difference between the surfaces. I'm not the mathematician, I'm not the electrician. All as I know is that you do get a difference, and from this difference, you can calculate the level of the cargo inside that double tube. Okay, and there's a fixed distance between the two probes throughout the entire depth tank. So in our case, the old ships that I was on, looking at about a 35 meter in diameter tank. You had a 35, the length of that tube was 35 meters, double tube, tube within a tube. Distance between those two probes was fixed, regardless of where you were in the length of that tube. And when you get this difference in potential across it, you then could measure the actual liquid level of the tank. Kind of an example, this is a very, very simple diagram of the capacitance center, tube within a tube. Go into your electronics, and it's transferred over to an actual level indicator. There's no cargo, liquid, or vapor released to the atmosphere during the level measurement, all enclosed inside the tank. So nothing ever comes into contact with the outside. Radar, been around for a long time. Now it's used to measure liquid levels on all sorts of liquid carriers. LNG, it's a very, very popular means of measuring liquid depth inside a tank. Operates on a high frequency, 11 gigahertz, and it's obviously used for liquefied gases and commonly used on LNG carriers. It's a closed device, just like the capacitance probe. Everything takes place inside the tank. Nothing, at no time does any vapor or any liquid come in contact with the outside environment. No liquid cargo is released during level measurement. And the level measurement is it's monitored all the time. That system is running all the time, so you always know instantaneously what the level of the tank is at all times. Ultrasonic uses the echo sounder principle. You're using a reflected sound wave, and you can calculate the ullage, which is the void space in the tank where there is no cargo, or you can actually measure the liquid of the depth, the innage of the tank, and this is all done by determining where you're going to locate your receiver. Sound waves are reflected from the liquid surface. Ultrasonic, you have a transceiver, it can be mounted either in the tank dome or at the tank bottom, whether you're going to measure ullage or innage. Doesn't, makes very little difference because from either one you can calculate the amount of cargo. They can be unreliable in gas carriers, and that I think predominantly is because of the actual movement of liquid within inside the tank. Very rarely do you have a tank that everything is static and there's no movement once. So you can get variable readings, and the readings can change with pressure and temperature changes. And this you really don't want. So you don't find them used that much on gas carriers. Are used other types. Each tank is going to be fitted with an independent high-level sensor. Every cargo tank must be fitted, and it must give an audible and visual alarm. The only tank that is excluded from this is a Type C tank. Those are the ones that we're looking at the high pressure tank, 150 psig, and having a capacity of less than 200 meters. So this includes your tanker trucks, which are your Type C tank. Okay, they do not have to have an independent high level. The independent sensor monitors the tank level, and it has a high level and high level alarms. Okay, as I said, you have two systems. You have one that monitors all of your tank levels, and this is the one where if the level gets too high, you're going to generate a high level alarm. If there's no response, what will happen is you're going to get a shutdown of the fill valve into that one particular tank. But you also have what's called this high level alarm, totally independent. And if that point is reached, it's a physical point inside the tank. If liquid reaches that point, you're going to generate a shutdown where everything's going to be shut down. That's going to close your manifold valves and everything, put the system into a safe position. This is required by the IGC, the International Gas. The second system we're going to look at is what's called the custody transfer system. And this is your volume measurement system, CTMS, custody transfer measurement system. And this is what calculates the volume of liquid inside of each tank. And each LNG carrier has to be fitted with a custody transfer equipment. And the system is a calibrated package of cargo measurement equipment. The cargo tank volume, when the vessel is built, is calibrated by an independent measurer. Usually this is done using lasers. The volume of the tank is accurately determined by an independent party. And from those readings, a gauging table is built, and you can go into this table for any level of cargo within that tank and calculate what the volume of the cargo is in that tank. Very accurate, and this is something that again is done by an independent party. So nobody has any gain. The high accuracy level, temperature, and vapor pressure measuring equipment system includes data logging and cargo calculation. The old vessels, the cargo calculation manually. In the gauging tables, you had your volumes, and you would have your levels, and you would calculate your volumes from those levels, apply corrections for list of vessel if the vessel happened to have a list, the trim of the vessel, whether the vessel was even keel, down by the head, down by the stern, because these all affect the volume of cargo within the tank. So all of these and also for temperature. So all of these calculations had to be done manually. Nowadays, all of these calculations are done automatically, very quickly. At the press of a button, you can find instantaneously what the volume of the vessel, volume of each tank. These custody transfer systems, as they're certified by this third-party agency, they're always approved by the local customs official. And the equipment has been developed in the practice in the LNG trade of relying on shipboard measuring equipment. The shipboard measuring equipment is because it is certified by an independent third party, and because it's accepted by all local customs, regardless of where you are in the world. The quantity of product transferred between the seller and buyer is always determined by the ship's figures. So when the ship arrives in a port, it does what is called a custody transfer measurement calculation to determine how the volume of cargo that's on board the ship. Cargo transfer is completed. Do another calculation to determine how much cargo remains on board the ship, and the difference is the amount of cargo that has been delivered from the seller to the buyer. These figures are accepted by customs, by the seller, and by the buyer. Quantities determined by the system are also used for import duties and fiscal accounting system accuracy is essential. Uh, Again, the import duties, this is where customs comes into play. So obviously these systems are very, very accurate and keep all parties involved happy. And that's the important thing. Okay, such systems include the following equipment. You have a level which is accurate to plus or 0.75 millimeters at a specified temperature over the full height of the tank. So you're looking at plus or minus 7 millimeters over a 35-meter tank. In the case of a spherical ship, in the case of membrane ships, you're looking at an accuracy of approximately the same over a distance of 25, 26 perhaps. Temperature is ranged from minus 150 to 170, plus or minus 0.2 tenths of a degree. In the range of minus 10 to minus 150, it's plus or minus 1.03. I think it's 0.03. And in the range of plus 80 to minus 200, 1 degree centigrade. So as you can see, the tolerances are very, very close. Okay, that middle one, I'm not quite sure what happened on that one. Your operating range is minus 150 to minus 170. These other ranges are out of your normal operation. You can see your tolerance is much closer to your actual operating temperature. Pressure is plus or minus 0.0015 bars. Pressure is close. Some LNG ships are fitted with devices that can measure the density. My experience with them is they're not as accurate as you would like to see them. So in most cases, density is derived from an analysis of the samples carried out at the loading terminal or at the discharge terminal. Gas analysis and then the density calculated from the gas analysis. When a cargo is loaded on board a ship, samples are taken and the samples are analyzed and the vessel will receive a cargo composition report telling them exactly what the components of the cargo are, and from those components, the actual density of the cargo is derived. And I believe someone had asked that question a little bit earlier in one of the presentations. So when you get to the discharge terminal, again, the discharge terminal will take samples. Usually, if there's a surveyor involved in the cargo calculations, they will also take a sample. These samples will be taken and compared, and this way everybody knows exactly what product is being delivered. Because, as I said earlier, this is it's a live cargo in the sense that it's constantly changing. So there will be a difference in composition from the time the cargo is loaded on board the vessel until the time the cargo is discharged, particularly in the international trades where you could have a considerable distance or a considerable amount of time between the load and the discharge. Calibration. Of course, your instrumentation is only as accurate as if properly calibrated. Okay? And calibration can be done on board by the crew using calibration instruments. Every ship has the necessary equipment on board to be calibrated, but there is usually an annual or a biannual calibration that's going to be done by service engineers using their own equipment. And this is just to recertify the gauging equipment on board the ship. This satisfies customs regulations and this satisfies the requirements of all parties involved in transfer cargo. If there's any anomaly, if there's any discrepancy, equipment can be calibrated on board by the crew using the instrumentation that's put on board the ship. In most cases, your calibration is done by service on a regular basis. Now, your calibration equipment, if it's on board, has to be calibrated also. So all of this stuff at some point in time has to be sent ashore to be calibrated in a laboratory and brought back on board. Calibration certificate that we know that everything is as it should. The ISM code, which is the International Safety Management Code, Chapter 9 of SOLAS recommends each ship carries calibration procedure that confirms compliance with the procedures available on board. I haven't spoken much about the ISM, and for those of you who are not familiar with the marine industry, uh, the ISM is something that has come about last 25 years. It has evolved, and essentially it began with the tragedy of the uh, ferry, the Herald of Free Enterprise, which was sailing from Belgium, Zeebrugge to, and the bow door, the vessel sank. There was tremendous. This was a tremendous tragedy, and up until that point, it was a ship disaster. Uh, the blame was always ultimately laid. You would find the cause of the accident and whatnot if there was a shortfall. If there was a shortfall of any type, it was going to say, well, the master was at fault, the chief engineer was at fault, the ship's pretty much where these incidents would end. But in this particular case with the Herald of Free Enterprise, uh, it was brought forth, became very well known that the vessel had complained about the uh, problems they were having with the bow door on this vessel, and they had notified the company management of this, and no action was taken by the. And when this became known, the courts held that not only was the ship responsible for this tragedy, the people on board the ship, they shared some of the blame, but the people ashore, the corporate people ashore, also had a responsibility. And this kind of opened the floodgates to litigation, and as a consequence, companies began to get very much involved in the safety aspect of ships. So nowadays, if there's a problem on board the ship and the ship notifies the company, action has to be taken, because if they don't take action, something happens as a consequence of that. Not only is the ship at fault, but the people who actually run the company can be held liable. So this has changed the safety environment of the industry drastically over the last 25 years. Uh, it began with the ferries. It then went into tankers, because tankers were problematic over the years with incidents and whatnot. It now extended beyond that. The cargo ships now also taking effect with passenger ships, and is now moving into the whole vessel segment of the industry. So ISM has become a very, very active participant, and controls a great deal of what happens in the industry now. So this is what this ISM is all about. It's the International Safety Management Code. Again, this is promulgated through SOLAS, through IMO, and has been very, very beneficial to the industry. Pressure monitoring is throughout the system is required by the gas code, and this includes pressure monitoring of your cargo tanks, pumps, discharges, compressor discharges, liquid and vapor crossovers. Anywhere that you can have a buildup of pressure, you have to have some type to monitor. You have to have some type of a device to monitor pressure, and you must have pressure controlled alarms and shutdown. This is all part of the integrated automation system of the cargo system, and this is uh, this is found on all LNG carriers, and we will also find it now on these LNG barges, these LNG barge articulated tug barge units. Uh, won't be like the it's not won't be like the old days where you're going to pull up alongside with a barge, and the barge just dumps fuel oil on board its ship. Now, in an operation that's going to be very, very closely monitored in all aspects regarding pressure, regarding temperature, regarding flow rates, etc. Gas code requires at least two devices for indicating cargo tank temperature, at least two in each tank. You're going to find that most tanks have more than two. You might just have one at the bottom and one near the tank top, but below the highest allowable liquid level. The highest allowable liquid level is going to be a level indicator, going to be either the high level alarm or the independent high level alarm. Actually shut a tank down, liquid reaches that point. So that temperature indicator has to be below that high level indicator for a tank. Right? Gas code requires at least two devices for entry. Okay, it's again, tanks requiring a secondary barrier at a temperature below minus 55 degrees. So you're not only are you monitoring inside your tanks, you're monitoring external to the tanks in the barrier spaces, secondary barrier. And these temperatures are monitored at all times because temperature would be an indicator of a potential leak. So you have to monitor your temperatures as well in your barrier space, as well as the insulation spaces. Okay, I do have a question I will answer. What kind of systems do you foresee to clean LNG tanks and lines? You do not have to. Do not have to. As I indicated when we had the picture of the inside of the prismatic tank, that tank could be just built or that tank could be 30 years old. That is the exact condition you're going to find when you go inside that tank and inside the lines. LNG is a very, very clean cargo. So you do not have an issue with cleaning any of the lines or any of the tank. Okay, let me see if I can pull that question down. Okay. Okay. Indication of leak detection within a pipe inner wall. Okay. Uh, Thank you. That's a good question. And usually, what you find is when your gas is transferred from the tank to the engine space, the piping from the fuel manifold or from wherever that LNG tank connects to your fuel system, from that point to the engine, the piping is going to be double walled, and this is required by code. It's a pipe within a pipe. The space between the two pipes is monitored by gas detection equipment. If you get a gas reading, in most cases, it's going to be 30% of the lower explosive limit. 30% of the lower explosive limit, which is 1.5% by volume. 30% of 5%. If you get a reading above 30% of the LEL, you will generate an alarm. And at that point, you are going to detect, you're going to try to find this leak. I have not heard of any instances where we have had a leak in this double wall piping engine room. All the years I've been involved in the industry. The actual location of the leak, this could be problematic. Could be problematic. I mean, I'm not quite sure how this could be. It could be done not with. Obviously, you're going to have to secure the gas to the pipelines, and you're going to have to find a secondary means of pressurizing this. I mean, if you can't see inside that double-walled space, it's going to be very, very difficult to find out where the leak is. So I think if this type of a situation were to arise, you would be talking about a gas freeing of that pipeline, and probably, I would suspect, again, I'm not sure, but I suspect what would have to happen is that entire pipeline would have to be replaced from point A to point B, because as it's connected as a single unit, I don't see how it would be possible to find out where the leak takes place in a double wall pipe. Once it's removed, obviously they could get it into a laboratory condition. They could probably find it. So that would be a challenge, and that's an excellent question. I hope that answered it. Gas code requires a temperature sensing device within the insulation or on the hull structure adjacent to the containment system. Okay, so your secondary, your hold spaces, your secondary barriers, your insulation spaces, all of these spaces are going to have temperature sensing devices. Just you just don't put one of these tanks together and say, okay, everything is going to be fine. There are temperature sensing devices, numerous temperature sensing devices placed throughout the secondary barrier, the primary barrier, the hold space, and these are monitored at all times. Any indication that the temperature drops dramatically, you're going to have a transitional temperature change, obviously, from the tank skin as you work your way through the insulation. But if you get a sudden drop in pressure, let's say, for instance, outside the second barrier, the temperature is going to be pretty near ambient, and all of a sudden that temperature starts to drop, you have a leak of some type. So temperature is an excellent indicator of any potential leak that you may have in your containment system. Again, the number of leaks that we have seen over the years, absolutely minimal. But these things do show up, and they do show up very, very quickly. Temperature is going to be, and also your gas detection. These spaces are monitored by your gas detection equipment. Uh, we'll touch on gas detection a little bit later, but you go through a series of points that get tested, and each point must be tested at least once every 30 minutes. So every 30 minutes, every point in the system is checked for gas concentration. And if the gas concentration exceeds 30% of LEL, you're going to generate an alarm. And once you generate an alarm, you're going to investigate and find out why are we getting an alarm. Your temperature sensors are oftentimes thermocouples, and they must provide a warning alarm prior to the lowest temperature for the hull steel being approached. Gas code requires at least 2 devices for indicating cargo temperatures. Gas code recommends more thermometers to be fitted, at least 1 tank to monitor temperatures during warm-up and cool down to avoid thermal. Again, what the gas code requires and what you actually have, you have numerous sensors, and these sensors must be monitored while you're going through a cool down process. It's a very, very methodical procedure, and it's very well documented, and you can start one of these operations and you can almost predict the minute when it's going to be completed. It's been time tested so well. So as you go along through these procedures, you're monitoring your temperatures, and if you begin to get any deviations and variations that you don't expect, you may have a problem, and now you have to investigate what's going on. Why isn't this temperature coming down? Or why is this temperature coming down too quickly? So not only are you concerned about something lagging, but you're also concerned about something that may be progressing too quickly. If you see things like this, you can make the modifications in your system that are necessary in order to do it in the controlled manner that you want to do it in. Thermal stresses are extremely critical when you're doing a cool down of a tank. The membrane tanks, thermal stresses are an issue, but they're less of an issue than they are with the spherical tank with that tremendous amount of mass of metal. That tremendous amount of mass takes a long time, and thermal stressors are a primary concern. But with either system, membrane or whether it's spherical tank, get down to about minus 130 degrees, 99+ % of all contraction of the metal has taken place at that point, and you can begin introducing liquid into tanks at that point in time. Gas code requires gas carriers to have a fixed gas detection system. It has audible and visual alarms. The system must be fitted in the cargo control room, the wheelhouse, gas detector itself, location. And with your bunkering systems, you're going to find you'll have a gas detection system probably at the bunkering monitoring station. Again, a lot of regulations are still in the evolutionary process. And I think what's going to happen is a lot of it's going to mimic you find an LNG carrier, transfer it over A lot of these things that we see requirements for LNG carriers, and most likely are going to become requirements under the IMO. These regulations will be promulgated as we go along. Somebody had asked earlier, well, gee whiz, doesn't the IMO do this? Doesn't the what's happened is again, this is an evolutionary event that we're dealing with bunkering. We have rules that have been established by the classification societies. You have DNV rules, you have ABS rules, you have German Lloyd rules, you have Lloyd's rules. You have rules in the port of Rotterdam, you have rules in the port of Antwerp, rules in the port of Singapore. Are all of these rules consistent? Most likely not. They mimic each other, they follow each other to a certain degree, but we haven't come up with a single unified code, unified rules and regulations. And I think what's going to happen is over a period of time, probably through the IMO, and these will all become international regulations, we're going to come up with some type of standard set of rules, and these will be accepted internationally worldwide. Ports themselves may have a little different, you might have to do one thing a little bit differently in one port than another. But for the most part, the rules themselves will be consistent, so that if you're going to take LNG bunkers on in Singapore, pretty much it's going to be identical to what it would be like if you took LNG bunkers on in Rotterdam or Houston or New York. And this is the end result of the involvement of IMO, obviously, in this particular area. So I think it's going to happen. We will see the integration of rules, somewhat of a standardization of rules on a gas detectors are normally fitted in the cargo compressor room, the electric motor room, cargo control room, unless it's classified as a gas-safe area. In most cases it is, but I've always seen gas detectors within the cargo control room regardless, and in enclosed space. Additional locations for gas detection equipment are hold spaces, except those containing Type C cargo tanks, inner barrier spaces between the tanks, airlocks. There are some areas on board the onboard vessels where you have to have an airlock where one door has to be closed before another can be open, and you will have gas detection in those areas. Burner platform vent hoods on steamships and boilers, and the engine room gas supply lines, and that's for LNG carriers only right now. And that's your double walled piping. Locations, our detector heads are fitted in locations dependent upon density of cargo vapors. So if we have a cargo vapor that's going to be heavier than air, you're going to fix your detectors at a low level. And if they're lighter than air, you're going to have your detectors at a high level. Most of your cases on LNG carriers, you're going to find your detectors in the overhead. Methane's lighter than air. And if it's in an ambient space, it's going to be warm enough where it's not going to be clinging. Sampling and analysis, samples are drawn sequentially from each detector head. The gas code requirement is sample intervals must not exceed 30 minutes. So as I said, once every 30 minutes, every space must be checked. And the alarm is activated when the vapor concentration reaches 30% of the LEL, the LFL, 30% of 5%, 1.5%. Don't get caught on these percentages here. Always bear in mind when you see these referred to, what are we talking about? Gas detector is 30% of LEL. LEL is 5%, so 30% of 5% is 1.5. In addition, each ship must have at least 2 sets of portable gas detection equipment, and these have to be adapted to the cargoes listed in the vessel's certificate of fitness. So if you're carrying LNG, you have to have a portable equipment that can detect methane, also ethane, propane, and butane, because those are components of LNG. So actually, you're going to have several sets of gas detection equipment, portable gas detection equipment. And each one of these detection pieces of portable equipment has to have span gas bottles. Span gas is a laboratory certified sample that's in a bottle so that you can calibrate your equipment a particular type product. In addition, each ship must have equipment to measure oxygen levels in an inert environment. If you have equipment that measures oxygen only, can have a problem if your hold space, say, is inerted or is full of nitrogen, trying to measure your volume of gas in that space. It has to be able to read within an inert background. Crew must know how to operate the gas detection equipment, know operating principles of the equipment. Again, we get the training, training, training. Crew it is checked on this on a regular basis. The ships I've been working on the last several years, this is a routine procedure to the point where over at a certain period of time, each member of the crew, each one of the officers has to demonstrate their knowledge in the operation of this equipment. So everybody is kept up to speed on these things. Because oftentimes if you're not using this equipment, you might not be as good at the use of it than you should be. So they're constantly quizzed on this stuff. And in all cases, manufacturers' instructions must be followed. And the equipment has to be tested at regular intervals. As I said, this is the process that they go through on the ship. Not only is the equipment being tested, but the operation of the equipment by the responsible people also being tested. And it's usually established by your company operating procedures, which are required by the International Management. Span gas, okay, I did touch on that a little bit. It's a mixture that's certified by a lab, has to be readily available, and has to be permanently piped if possible for fixed gas detection. Span gas to test it permanently. For your portable systems, you have a small span gas bottle that you use for your portable detector. Instruments and monitoring equipment help LNG handling process run efficiently and safely. Again, safety, environment, safety. The IMO establishes gauge standards which cover a full range of gauging systems, and standards must be strictly followed. Electronic sensors, however, must be monitored closely by operating personnel. All of your monitoring points are monitored automatically and electronically, but this doesn't mean that you can't just ignore what's going on. Your operating personnel, your cargo officer, gas engineer, your officers, these people are constantly in and out of the cargo control area, looking at the various systems, checking. So this is something that doesn't get put on automatic, and we're going to walk away. Even though these systems operate very reliably and very, very efficiently, the human element is still critical. It's still very, very important. Okay, and that's pretty much it. All right. Okay, Jared, are you there? That's a wrap on 3.6.
Okay, sorry about that, John. I'm here. I clicked on the wrong mic here. Thank
That's
you.
okay.
Thank you for today's lectures. Very enlightening, and I know we have you for a couple more days, so that's great. Just a couple of administrative items.
Yep.
We've sent you over now all of the PowerPoints to the students, so those should be available. They're in a PDF format, 3 slides, note page style. We also sent over the MSDS as well as the history of LNG. So those documents are attached as well. And the last one was a link that you would like the students to take a look at, minute 0 through 5 and 17 through 24, I believe.
Yep.
So in addition to that video, which I recommend you watch the entire video if you have the time. I know we've been here most of the day. But also look at the video links that are associated with today's lectures that are on the list from Josephine's email from last week. I recommend, just to really drive home the points that were discussed today, you can see some video, and it might connect some of the dots for those that are still unsure. I think tomorrow we'll begin at 0900 Swedish time. Please try to make it. It's very early for John. He's coming in from Connecticut. So if you see his clock there in the back, it was 5 a.m. I believe is when he began today. So
Yeah, today wasn't bad. It was 5 a.m.
it's going to be 3 in the morning tomorrow. So please give him a bit of a break. He might be red-eyed and slow speaking to start the day, but
Yeah, I won't need, I don't need any questions at 3 a.m. Thank you.
Excellent. Okay. Well, if there's not any other questions from our group here, anything from you guys? Nothing from us here. I'm sure there's going to be some questions as this kind of settles in tonight, and we'll pick it back up tomorrow at 9 in the morning. If there's any questions, please email Josephine this evening, and we'll try to square it away tomorrow morning before we begin.
Yeah, good. Sounds good.
Great. Okay. Thanks, everyone. Appreciate it.
Okay, everybody have a good evening over there.
Thank you.